Hello everyone, welcome to this presentation. So this is a joint work with Professor Rupesh Nasir from IIT Madras. So currently I'm a postdoctoral researcher at Concord University, Montreal, Canada. Why is this research relevant? Software nowadays keeps on getting updated, but along with the updates, the programmers or the developers unknowingly introduce some bugs. The manifestation of the bugs can be very costly. So some of the examples that we can see as displayed in the slide are classical examples of software failures. To detect those things, what we need to do is to do program testing using certain input combinations that can actually drive the program to exhibit this type of failures. Why regression test prioritization? So we see that there are two versions of the code. So there is a change in the if block. So some of the test cases, which are the inputs, will pass through the if and the others through else. So the small sigma is the selected test suite. This is a set of test cases. Now this is another regression test suite. So these three test cases will fail. In the optimal prioritization, all the test cases, starting from the first test case, all the failures are compacted from left. That means they occur consecutively. We need to have some prioritization heuristics so that we can move close to the optimal. So RTP, regression test prioritization, has been there since the 1990s. But what the existing heuristics do not consider is whether the impact of the code that has changed, that I'm calling delta, whether the impact of the delta is observable at the end output of the program execution for a given test case. So this is how it happens. So there is a test case which reaches a fault site, so that we call fault activation. So it reaches the fault. Now that fault infects the program state that leads to an incorrect program state. This incorrect program state needs to propagate to the output. Now here comes unwanted program states, intermediate program states, because this is not the output, because here it lies in the path of the propagation. So output and final program state. So the bigger circle is outputs and final program state of variables. A subset of these is observed program states that can be observed, which are not lost due to computational masking or due to interference among different program states. Incorrect program state should go to incorrect final state, and that incorrect final state should intersect with the observed program state. So observed incorrect final program state is where we observe that the test case has failed. So we see that the yellow arrows are intermediate in between the red and the green. So if the whole path is followed, then we can detect the bug. So if this green path is not followed, the error state has failed to propagate to the final state, and this we call as failed error propagation. We have a source code on the left, and from the source code, you obtain the control flow graph, CFG. Basic blocks that are highlighted, that is in the orange color, are the affected basic blocks. That is, some statement got changed. Now, since control flow graph is static and is a finite representation and is unaware of the input, the test case, not useful for the white box test case prioritization, because it actually over approximates that. It is not going to represent the dynamics of the execution. So what we want is a basic block trace. Trace is dynamic and is input dependent. So for each trace, that is for each test case, that is the sequence of basic blocks in the older version. So how do we do that? So here comes the notion of the delta displacement. We have the sequence of basic blocks, B0, B1. So here the basic blocks highlighted are the affected basic blocks, that is the capital delta, which is a set, delta 1 to delta m. So there are m delta basic blocks. We actually go for the loop-free in-order sequence. This is a trace. So there can be multiple occurrences of a same basic block. Actually keep only the first occurrence in sequence. So that is loop-free, and the relative order between the different basic blocks are maintained. And B0 to BR minus 1, that is the whole trace, not only the affected basic blocks, but whole basic block trace of the program. Tri-partition this sequence. So left, right, and middle. So in the left partition, which is of length A, that hop distance length A is the reaching distance of the first affected block from the first basic block that is that appears in the trace. So imagine that we have accumulated all the affected states up to the last affected block. We want to transfer the error state to the output basic block. There is a final basic block. So we want to transfer that as fast as possible. That displacement is given by C. What about the intermediate basic blocks? So there can be intermediate displacement. So intermediate separation between the basic blocks. So between the first and the last, the distances, intermediate distances, we take the average and we take it as B. So ABC is a displacement triple. So we call this displacement triple, which actually tripartites the loop-free in-order basic block coverage. That is the trace of the test case for the older version. Because in the new version, we have not executed the test case yet. So ABC is the delta displacement triple for the regression test case TI. Now, the lesser the displacement means there is not much path traversed in the program execution path. If we say that there is a lot of path traversed, that means there are a lot of sequence of instructions. So the lesser the number of instructions encountered, the lesser is the chance of masking. That is our heuristic. How do we calculate the displacement value? Eval a plus 1 into b plus 1 into c plus 1. Plus 1 is the correction factor because the first affected block b0 can be affected as well. In that case, the displacement is 0. To correction the 0 factor, we include plus 1. Now, we have a multiplicative combination. We want this multiplicative combination to be as less as possible. So the displacement, so this should be as less as possible. The scattering should be as less as possible. And the propagation distance from the last affected block should be as less as possible. So dval should be as less as possible. Now, for different test cases, this is for TI. TI and TJ, it might be the case that two devals are the same. In that case, what we do is we actually go for how much of the delta coverage of the basic blocks. Actually, enforce a tiebreaker, and this tiebreaker is actually another heuristic, that is greedy total. Priority of a test case TI is actually proportional to the number of affected basic blocks covered. The higher the number of basic blocks, affected basic blocks covered by a test case, even in the case of a tie, the test case that covers more number of affected basic blocks is given priority. So that's how the priority is broken. Now, we see that we have a conflicting scenario here. So dval should be as less as possible. So lesser the value, higher the priority, and this should be as high as possible. So we normalize it by dividing by the delta, all the affected blocks. So this is between 0 and 1. So it takes the complement. So the sum total of dval and rel. So dval plus rel is the sum total, that the summed value is actually the priority value for the Colosseum heuristic. That is our approach. So we hypothesize that a regression test case path with a shorter overall displacement, that is multiple recombination, has a good chance of propagating the effects of the code changes to the observable outputs. And we prioritize the test case with smaller overall displacement. Intuition is that the probability of a test case revealing a regression fault depends on the probability of the corresponding change propagation. And this is how we extend this logic. Delta displacement provides an approximation to failed error propagation. So we evaluated how this approximation works in practice. We selected some C projects, 20 C projects, open source C projects, some of them from the SAR repository. Some of these are classic examples used since the 90s. So, and there are also GitHub projects, 8 GitHub projects. Here we see that there are a total of 260 version pairs and 80,338 delta basic blocks overall, considering all the versions and all the benchmarks. And the total of source lines of code, we have 694,512. Most importantly, we have 70,000 test cases to exercise the faults. So Colosseum versus state-of-the-art approaches. So on the y-axis, we have the effectiveness value. That is, it lies between 0, 1, 1. The metric that we have chosen is APFD, average percentage of faults detected, which is a very popular metric. So the higher the value is, the value that if it is closer to 1, it is fruitful prioritization or it is effective prioritization, which has a higher fault detection rate. Now here you see that APFD, this decreases along the y-axis as we go right. So this is the budgeted APFD. So normalized APFD, NAPFD. So APFD 100, that is the APFD of executing the top 100 test cases, or that is executing all the test cases. If normalized APFD of that is the APFD of executing the top 90 test cases and then the top 10 test cases at the right. So we see that the blue curve for Colosseum, when compared with all the 4 state-of-the-arts, that the relevance is the black one, that is greedy total. Greedy additional is the red one. So this relevance, that is greedy total and greedy additional, has long been used since the 90s as state-of-the-arts. And another state-of-the-art is the green one, that is ART, adaptive random testing, which has feedback directed random testing. And green one is a RELCON, which is a combination of relevance and confinements, which is one of our previous work. So we see that according to, even in the low budgets, Colosseum actually outperforms all the others. So Colosseum is more effective than the state-of-the-arts and the competing approaches, even at the low budgets. Now, how about the efficiency? So if we have n test cases, R total basic blocks and M affected basic blocks, as the M delta basic blocks. And the time complexity is order of N M R for Colosseum. And it is comparatively efficient with the relevance and railgun. So relevance, so greedy additional and railgun and art. So art is hugely expensive because there is feedback directed random testing. So it's more than exponential, it's cubic, there's a number of test cases. And also additional, greedy additional and railgun, they have quadratic factors in N and N. Comparatively, its efficiency is comparative with greedy total. Thanks for attending this presentation, and I'll be happy to take on questions now.